Okay, thank you. Well, my name is Carolina Seguí. I started my research at Duke University in North Carolina with Professor Manolis Veveakis in Landslides. So I graduated in geomechanics. We followed the start of landslide research from the late Professor Ioannis Vardoulakis. And I have been in RWTH in Aachen, Germany, doing postdoc, continuing my research in landslides. And now I am in the University of Barcelona in Spain, also continue my research, but with actually one landslide that I will show you now some the results and some tests. But we got more core data, core samples, so we are working with that right now. Hello, thank you everyone. My name is Carolina Seguí, and today I will present you part of my research, which I did with my supervisor, my thesis supervisor, Professor Manolis Veveakis, continuing the work of the late Professor Ioannis Vardoulakis. So, which is called continuous assessment of landslides by measuring their basal temperature. So I will do a short introduction. So here we can see a wall map, which is a repository from NASA of all the landslides recorded, that have been recorded in history, which are over 10,000 landslides. And from all of them, they have caused over 38,000 fatalities. So the main triggering factors of these landslides is mainly around 70% is triggered by groundwater level variations due to rainfall or, for example, dam construction nearby. So this is another study that of the projection of losses from natural hazards, and what we obtain, what we get here is that actually the landslides are the ones that can actually be mitigated if we use preventive measures. So these rely on our ability to forecast and control the response of the landslide to the external loading, as I said before, these groundwater variations. So now introducing our work, we focus only on deep-seated landslides. This is an example of a deep-seated landslide. This is the one profile of the Bayonne landslide that collapsed in 1963 in northern Italy. So the main features of deep-seated landslides are first that the sliding mass moves as a rigid block over a thin basal shear band or sliding surface, which is located usually below 10-meter depth or below the roots of the trees. And it can be up to hundreds of meters depth. So these type of landslides can be rotational or translational, depending on the shape of the sliding mass, on the shear band. And the main feature of these landslides is they have a large phase of very slow movement, which is called creeping, during years or tens of years until they suddenly collapse catastrophically. So this diagram shows the life of a deep-seated landslide, if I can say that. So first, there's a short period of primary creep, which is when the landslide starts accelerating. Then there's the largest period here in the middle, which is the secondary creep, where the landslide moves very, very slowly during years or tens of years. And finally, there's the tertiary creep, which is the last part, which is the last acceleration and the catastrophic collapse. It is very important to say that once the landslide enters in the phase of tertiary creep, even if we take remediation measures, the landslide cannot be stopped. So to understand better the mechanism of why the landslide turns to secondary to tertiary creep, we focus on the critical parts of a deep-seated landslide. The first one is the eroding toe. For example, if we have a river, it removes mass from the toe, which is the stabilizing part of the landslide. Then there's the deforming shear band, where all the kinematics happen, and then the groundwater level variations inside the sliding mass that gives extra loading to the shear band. So in our work, we will focus on the deforming shear band and the groundwater variations inside the sliding mass. It's important to understand that these deep-seated landslides are very violent and catastrophic. And I remind you again that once they enter the tertiary creep, they cannot be stopped even if we take remediation measures. So now I will explain you the mathematical model we use that we couple the external loading, so the groundwater variations, with the internal response. So how the material of the shear band behaves, which we have called the Veveakis forecasting model in honor to the late Professor Ioannis Veveakis. So this model has this mathematical model has three conceptual models of the landslide. The first one is a 2D profile of the landslide, where we perform a limit equilibrium. In this case, it's a two-wedge method for simplicity, because the goal is to calculate the shear stress of the entire part of the landslide with different groundwater levels inside the sliding mass. So once we obtain this shear stress, we convert it to an infinite rigid elastic block for simplicity for the model, where the stresses calculated from the model A are admitted in the basal shear band, which is our conceptual model C, where we can see the velocity profile along the vertical profile of the vertical section of the shear band, and also the evolution of the temperature along the shear band. So now moving into the mathematical model, we will focus now on the behavior of clays, because most of these deep-seated landslides, their shear band is formed by clays or clay-like materials. And Professor Veveakis postulated that clays, they consider that clays are fully saturated in water, perfect viscoplastic material, and that they are velocity hardening, meaning that when you increase the strain rate, or your shear stress increases. And they are also thermal softening, meaning that when the temperature increases in the material due to the friction, because of the acceleration of the landslide, your friction coefficient of the material decreases. Therefore, the velocity hardening is a power law where at the exponential, this n is the rate sensitivity of the material, and the thermal softening is an exponential law with m, that is the thermal sensitivity of the material, theta is temperature, and theta 1 is a reference temperature from the field. So Professor Veveakis ended up with an equation of the friction coefficient at critical state that combines velocity hardening and thermal softening. So now moving forward with the mathematical model, with this viscoplastic shear band, we take as a constitutive equations the shear strain rate that considers the shear stress, the rate, the strain rate, the rate sensitivity, and the ratio of thermal and rate sensitivity and the temperature. We also take the general form of heat diffusion equation, and we also perform a momentum balance for clay, where in the horizontal direction is driven by the shear stress, and in the vertical direction by the normal force. So what our goal is to study the stability of these deep-seated landslides. To study the stability, to see if we are in the second, so in the phase of secondary creep or in tertiary creep, we take the heat diffusion equation I just showed you, and we pass it to dimensionless form for simplicity, where this equation depends on two parameters, the Grunfeld number and the temperature at the exponential. This Grunfeld number is a dimensionless number that takes into account all the values from the material of the shear band, and ds is the thickness of the shear band, and also the external loading that we calculated in our conceptual model A. So now to study the stability, we take this heat diffusion equation in dimensionless form to a steady state, so equal to 0, and with applying the pseudo arc length continuation method, we obtain this steady state curve or Bratu curve, where we plot the Grunfeld number and temperature in time of the landslide, which is equal to the external loading with the shear band temperature. So how we interpret this, this curve? So here we have the peak of the steady state curve and the maximum value of Grunfeld number, which can be stable. And then if, for example, in our landslide, the Grunfeld and the temperature are within the gray area, the lower branch of the steady state curve behaves as an attractor and the landslide is stable. However, if the Grunfeld and temperature are go outside this gray area, the landslide is in tertiary creep, meaning that the landslide catastrophically collapses. Therefore, our goal is to maintain the behavior of the landslide with the Grunfeld number and temperature within the gray area. So now we want to test the mathematical model and also the effect of the temperature playing an important role in the stability of the landslide. So we took a field case study, which is called El Forn landslide. This landslide is located in the southwest of Europe, in a very small country between Spain and France that is called Andorra. This landslide, you can see here, very large landslide, is about 300 million of cubic meter of rock mass that is sliding towards the city of Canillo. But inside this large landslide, there's a small lobe around 1 million of cubic meter of rock mass that slides faster. And here we can see from the S10 borehole that has been instrumented the inclinometer data of this lobe, where we can see that it moves as a rigid block, meaning that is a deep-seated landslide, and the shear band is between 29 and 29.5 meter depth. So the material of this lobe is mainly formed by black shales and limestone of the Silurian period. And here we have the core samples that we have tested in the laboratory, and where we have found, apart from the inclinometer data in the experimental test that I will show later, that the shear band is between 29 and 29.5 meter depth. Now, here is an example of the remolding of the samples and the final shape of these samples for testing them in the thermal triaxial. It is important to note that we have divided the depths of the samples for at each half a meter. So we perform an experimental campaign in a customized thermal triaxial machine that we have at Duke University. And these are, because they are core samples, the material is very limited. So we did exactly the same test for all the samples outside and inside the shear band, because we wanted to find the rate and the thermal sensitivity of the material. So what we did is 2 cycles of loading and unloading to remove discontinuities inside the sample and let the sample reach critical state. Once the sample reached critical state, we started the velocity stepping to find the rate sensitivity of the material. Once we have this part of the test done, we let the sample reach critical state again, and we start increasing the temperature of the sample to find the thermal sensitivity of the material. So first, I will show you the results for the rate sensitivity. We have found that outside and inside the shear band, the results are exactly the same. We have a power law with the same value of rate sensitivity, which is 0.0135, sorry. And we can see that these results are very similar to the ones that Leyenhügel obtained in 1974, also for clay material. And the value of rate sensitivity is also very similar. Moving on with the thermal sensitivity, we found that we obtained the same exponential law, but with different values of thermal sensitivity from outside the shear band, which is the orange one, with a value of 0.0136, and that inside the shear band, the thermal sensitivity was higher, with a value of 0.04. So because we found that the rate sensitivity is exactly the same for outside and inside the shear band, but the thermal sensitivity is different, then we did micro scale tests to try to understand why we obtain these results. So we perform SEM EDS tests to see the fabric of the mineralogy of each sample. Then we also perform X-ray diffraction to see the mineralogy, micro-CT tests to see the porosity, and also plasticity index tests. So what we found, I highlighted here the center of the shear band in red. So what we found in terms of fabric is that outside the shear band, the minerals are randomly oriented. The phyllosilicates are face edge contacts, and they are very folded also because they are shades. But as we get close, right above and below the center of the shear band, the minerals are starting aligning, and the folds are smoother. And at the center of the shear band, all the minerals are completely oriented parallel to the shearing direction. So the mineralogy we found was between 20 and 30% of quartz, and then between 70 and 80% of phyllosilicates, that they include muscovite, chlorite, and paragonite. Then what we found is that the porosity and the plasticity index have the same behavior in depth, meaning that outside the shear band, they have average values, then right above and below the center of the shear band, the values are smaller, and at the center of the shear band, the values are higher. These two, right above and below the shear band, is because the reorientation of the mineralogy and also the pressure. And this is due to the completely alignment and contacts face-face, which are weaker than the face-edge contacts between phyllosilicates. And this is the displacement that I showed before from the inclinometer. So this is a sketch that I did to represent more or less roughly the evolution of the fabric from outside to the center, outside the shear band to the center of the shear band, which we call area of intense deformation, which is, as I said, completely aligned. The mineralogy is completely aligned parallel to the shearing direction. And I also need to say that the exact thickness of the shear band is unknown for this case study. So now that we obtain all the results, we can answer the question on why we had the same rate sensitivity from outside and inside the shear band. And it's because we have the same mineralogy in all the samples. However, with the thermal sensitivity, the difference of the values, we can see that the behavior is the same in depth, is due to the fabric, the orientation of the mineralogy. So it is very important to see very well the contact between the minerals. Because as I said earlier, if we have face-edge contact, it is a stronger contact that you need to apply more pressure to create movement. However, if you are face-face contact, you need less pressure, and it's easier to accelerate the landslide. So now to test to validate and test if actually there's any change in temperature when a landslide is accelerating, we instrumented this lobe here in the S10, where you can see here better. We instrumented with UPC, with Polytechnic University of Catalonia in Barcelona, 3 piezometers, 2 above the shear band and 1 below the shear band. And we from the university added a thermometer at the center of the shear band. So the data shows that here is the water pressure from this piezometer, where we see that is empty. There's no water. However, below the shear band, there's a lot of water pressure, meaning that there's a pressurized aquifer below that is the one that drives the landslide and accelerates it. And this is probably because the shear band creates an impermeable layer that doesn't allow to have a free aquifer. No? So here we also have the temperature data from the thermometer. And I also need to say that the piezometers also measure the temperature, where we see that it's mostly constant in time. However, in the thermometer inside the shear band has a lot of variations, which now I will show you that they follow very well the behavior of the pressure from the pressurized aquifer. So now that we have the field data and the experimental data, we apply everything to our mathematical model. Remember the heat diffusion equation in dimensionless form with the Grunfest number and the temperature at the exponential. So the input data that we apply to the model is the field temperature and the water pressure from the piezometer below the shear band. And here we have our stress equation to calculate the shear stress. And then we also have the rate and thermal sensitivities from the experimental test that we perform in the customized thermal triaxial. And here we have the Grunfest equation. This is a bit different because we have here the initial Grunfest number equation, okay? Because for each case, you always have lags of different data. And for this field case, what we lack is the reference shear stress, even though we can have a range of values due to the depth of the shear band and the material that we have above the shear band. And then we also don't know exactly the thickness of the shear band, but we have a range of values because of the SEM test that we perform, which is less than half a meter. So because we don't know the initial Grunfest number, we perform a Monte Carlo method for 500 simulations to calculate G0, comparing, calculating the temperature and comparing it to the field temperature, obtaining a very good fit with this value of G0, of initial Grunfest. So now that we know more or less this thickness of the shear band, where we observe it from core logs and this microscale test that I show, we also know more or less a range of expected reference shear stress due to the depth. We calculated with an inversion of values for thickness and reference shear stress for different values of thermal sensitivity, okay? To try to understand which value first of all, if we need thermal sensitivity in our model, meaning that the temperature plays a role, and also because we obtain different thermal sensitivities, which thermal sensitivity would be best to get to obtain most fitted to the reality. No, so here we have the calculation of the model for without any thermal sensitivity, and we see that the range of values of the shear stress for the expected thickness of the shear band is completely out of the scope from the depth that the shear band is. Then if we calculated for the thermal sensitivity, we obtain outside the shear band, and we see that for the expected thickness of the shear band, the reference shear stress is also high for a 30 meters depth. However, for if we take the thermal sensitivity of 0.04, which is the one that we obtain at the for the samples at the center of the shear band, we obtain a very good fit for the expected reference shear stress. Therefore, we can see that actually we need to take into consideration the thermal sensitivity, and also which one, if outside or inside. And as we can see here, we need to test and obtain the thermal sensitivity from the material inside the shear band of the landslide. Now, with all the values obtained from the inversion of the model, from the field, from the experimental test, we have here the forecasted the field displacement in red, the cumulative field displacement from the extensometer that was installed, and we also calculated with all the values the forecasted displacement. And as we can see, we have a very good fit. And finally, the goal is to plot everything in our phase space to see where we at, if we are close to the tertiary creep, so outside this this gray area, or if we are in a safe space, meaning that we are far from the gray area, from the white area. So here, what we did is this dashed line in purple is the pressure, the water pressure from the piezometer below the shear band. And here we have in the dashed line black dashed line the field temperature, where we see that the variations of either both the water pressure and the temperature follow very well. They have more or less the exact same behavior, meaning that the material is very responsive to pressures, to external loadings, and then we calculated the temperature in the model with all the values. So we calculated the temperature in the model with thermal sensitivity and without thermal sensitivity. And we see that we have the exact same values. But when we plot it into our phase space, room phase number normalized temperature, or is equal to external loading to shear band temperature, what we see is that the red one is with thermal sensitivity that follows the lower branch of our steady state curve, and that the blue one without thermal sensitivity is not following the steady state curve. And also, if we extrapolate the behavior, we see that it's unconditionally stable, meaning that if we don't take into account thermal sensitivity, the landslide would never collapse, which is impossible. Therefore, here we prove that actually the thermal sensitivity is necessary. And finally, what I wanted to show you is the Veveakis forecasting model applied to different case studies that are mapped in the same phase space, normalized pressure, and normalized shear band temperature. So there are 4 case studies plotted here. The first one, so we have 2 that already collapsed, which is the Bayonne landslide and the Mud Creek landslide that collapsed in 2017 in California. And then we have the 2 landslides that remain stable and they are still creeping, which is the Shuping landslide in the Three Gorges Dam in China, and the one from El Forn, which is the red one, which is still very stable. So this is what I wanted to show you, that first, the temperature, we see that is imperative to have it and to control it, to have a better understanding of the mechanism inside the shear band and why the landslide behaves, how it behaves into the external loading, knowing very well the material that forms the shear band of that landslide. And also here you can use this phase space to map where your landslide is, if it is far from collapse or if it's close to collapse. So you are able to take remediation measures, meaning that maybe you can remove water, lower the reservoir level if the landslide is driven by variations level from the dam, etc. And thank you very much for your attention. I will be happy to answer any questions if you have.